Hello. Uh, Hope I'm audible. So, yeah. So I realized after I had an internet issue last week, and for which I could not take my class, and I took a makeup session for that on Friday morning. So the session recording is available on YouTube, and so I believe you've shared the YouTube links. So unfortunately, what I realized later is that uh, the content that I had covered in that session uh, was not related to week 4, which I was supposed to cover, but it was related to week 5, which is this week. Uh, so, so if you are here, I can see a couple of new students here who I have not seen earlier, University in Ramjana. So I'll just paste the YouTube link in the chats, and I think you'll also get it from NPTEL pretty soon. So you can go to this YouTube link and see this video. This video contains a discussion on this week. So whatever has been covered this week, so fading channels and Gaussian fading, Nakagami fading, different kinds of fading, and so all of that discussion and related problems I've actually already covered in the previous session, which I took on this Friday, and so that is already there, and it's available on YouTube. So you can go and check. Uh, so the reason I'm saying this is in today's class, I was thinking of doing more of a revision of the previous week and this week. So since previous week's contents, I have not done a discussion, so I would focus more on that. But even in this week, if there is something that you would want me to discuss, because actually I was supposed to cover this week's content this week. Oh, 1 second, I'm getting a call. I'll just pause for. One second. Am I audible now? Can someone confirm if they can hear me? Okay, thank you. So yeah, as I said, I'll just 1 second. I will paste the link in the chat again. So by mistake, so in the previous week, I should have covered week four's content, which is a more basic discussion on um, like on on shadowing and Doppler effects and all of that, and the very basics of Rayleigh fading. But unfortunately, by mistake, I skipped that, and by mistake, I skipped that, and I covered week five's content instead. So, um, so that was a mistake on my part, because last week I couldn't take my class, and I took that session in this week instead, on Friday, because of some technical issues. But so I'm just pasting the YouTube link in chats again. It will be shared with you by NPTEL later. Yeah, just a second. So you can go to the link to figure out whatever was covered regarding this week. I'll just be back in a minute. Hello. Hi. I hope I'm back. And okay, this test is okay. This is perfect. I'll just close this and go to my usual app, which is OneNote. Heading document. Creating document shadowing. So okay, so I'll try to do a summary of both of the weeks, week four and week five, and I hope you can follow. But if there is anything specific that you want to ask, I would be happy to address. My technical issues are now sorted. Uh, so yeah, anything that any specific questions? Otherwise, I'll start. Right. Uh, so so as I said, so in second. So in the previous session, I covered week five. So as you can see on the screen, so all of the questions that are relevant to this assignment, I have actually uploaded the notes already on my Drive link, and this discussion is there on my YouTube channel. But I'll definitely go back and refer to them if you need any help with any question. But I'll first try to cover the previous week's content because that is what I missed, and and then come back to this week. So let me first start with a simple question. So one of the questions here was, so like some curve like this, right? So you are provided um, one. So this is received power. So here you have received power. this is distance from transmitter, right? And your receive power is typically in dB scale. I'm just writing it in dB. So you have three lines here. One is straight downward sloping. Another is a solid downward sloping line. And another is like somewhat like this, right? So the question is, so let's say the straight line is A, and the round line is B, and the more wiggly line is C, right? So question is, which so let's say you are given some kind of match the following, right? Match the following. So you are given A, B, C here, and then you are told large scale, small scale, and then so I'm writing this as large scale as LS, small scale as SS, and then you have LS plus SS, right? So so can somebody answer this for me? Okay. Oh, sorry. I think it went out of view. Can somebody answer this for me? So you have three lines here. One line is just a straight line. The first line is A, and second line is B, which is kind of like a sinusoid, and the third line is um, like very very fluctuating random kind of thing. Um, so okay, small scale, but which one is small scale? So I want you to complete this matching. Let's say, okay, so what is A? Can somebody tell what is A? So I want you to like do this matching. And here, let me write this as 1, 2, and 3. So A corresponds to which of 1, 2, and 3? Similarly for B, and similarly for C. Okay. So here the answer is actually A stands for large scale, B uh, B is actually, I believe, C is small scale, I think, and this is something like this must be small scale plus large scale. This should be the answer. So, what is the difference between large scale and small scale? So, in large scale fading, large scale fading depends only on, so LS is, LS depends only on path loss plus shadowing, right? So something like that. And right. Then you have small scale. It's just random fading. Right. So might be slightly mistaken in the way I've drawn it here. 1 second. Actually, I should change it. Let me make large scale actually has two parts. So let me just write it this one as instant path loss, shadowing, and fading. Right. So uh, so typically path loss is A is path loss because A varies the least. Right. Then I think it's direct relation. Yeah. A is 1, B is 2, C is 3. A is path loss because A decreases directly with the distance and it depends on nothing else. So it's just a linear downward sloping line, straight line with the distance in dB scale. So that is exactly how path loss behaves. There is no dependence, no randomness on any other factor. So this straight line is your path loss, right? Then your second line, which is somewhat random, it uh, it is like somewhat like sinusoid, and actually no, that is somewhat like sinusoid. So that is actually fading. So hmm, yeah, I'm confused, but so A is path loss, B is uh, B, sorry, B is shadowing because B fluctuates a little less randomly, and it is a function of distance also. So that is typically shown by shadowing. Shadowing effects are more visible uh, closer closer to closer to the source and less as you move far away. And the third one is fading because fading is completely random. Fading doesn't depend on any location, and it is the nature of the propagation environment. It is completely random. So fading is this most fluctuating part, right? So the most stable, the most linear behavior is shown by path loss. Then you have shadowing, then you have fading. And 1 plus 2, path loss and shadowing combined actually is called large scale fading. And then this is actually called small scale fading. Large scale, small scale. So this kind of if you see a plot, if you see a general plot, you should be able to figure out which plot corresponds to which phenomenon in the wireless tunnel. Okay, this is one. Second one, uh, so over here, let's see. Hmm. So this is actually my bad. The second option should be, if I denote this as PL, this should be path loss plus shadowing. And this third option should be, so this is PL plus S, PL plus S plus fading. So that's how it should be, because as you can see, it's kind of superposed on top of each other. So first you have the path loss, and then if you apply shadowing on top of path loss, then around this mean line, which is a straight downward line, you have log normal shadowing, right? Log normal shadowing with a mean of 0. So log normal shadowing will add on top of this mean line, and so it will cause these slightly bigger perturbations in the large scale fader. And then you have these squiggly these small lines, which are actually random fading events in the environment. So then it just fluctuates very randomly. So that is small scale fading. So essentially 1 and 2 are both like to comprise large scale fading, and the third comprises large scale. Third one comprises large scale plus small scale fading. So that is how you will understand this kind of a diagram. So you first, if you know the distance from the transmitter, you first calculate the large scale fading, then you apply log normal shadowing. So you add the shadowing term, and then there is this random fading coefficient, which you multiply, which you also add in dB scale you add, and so then it fluctuates even further. So that is how you kind of pictorially understand all of these three factors that affect channel gain. Okay. So now after this, let's try this problem where you are told that any questions? Any doubt? Okay. So in the next kind of question, let's say you are told that at the receiver, the received power at a distance d, right? It is at the receiver, received power is given as something like 1.05 times 1.05 times P min, where P min equal to receiver sensitivity. Right? So this is the average power. So so your question is, you are told that there is log normal shadowing with sigma equal to 3 dB. That's a standard deviation, right? Then you are asked what is the, let me make this a little bigger, 8 dB, let's say, or 2 dB maybe. Okay, let it be 2 dB. Then you are told what is the probability of outage in this situation. What is the probability of outage? So how do we calculate something like this? Right? So you are told that this is the average received power, right? So typically So if I take 10 log on both sides, so why am I taking 10 log? It will become clear in a moment. 10 log Pmin. So the reason for taking 10 log here is to compute the difference between the average received power and the minimum received power that I need. Because remember, Pmin is receiver sensitivity. So the receiver is designed in such a way that it can detect signals only above a certain threshold, and so that threshold is Pmin. And so I can define a margin beta, which is equal to 10 log of the average received power minus 10 log of the minimum received power of the receiver sensitivity, which comes out to be. So somebody can calculate this and tell me. Let me try with my calculator. I'm getting the answer to be 0.212, something like this, right? Why am I calculating this? Because I need to compute something known as fading margin. Fading margin. So what is the fading margin? Fading margin is defined as this quantity. So I'm trying to see how much value I should add to the receiver sensitivity, right? So that I can account for possible fading in the system, right? Possible fading in the system. So how do I account for that? That is accounted by this beta term, right? And so this, okay, just to clarify, this is at the cell edge. So you are in a cellular system and your user is at the very edge of the cellular system. And this is the average receive power you are getting, right? So this margin can be breached if there is like you don't want your shadowing to be greater than this margin, right? So your outage probability is essentially, let's see. So receive power is this, right? So on top of receive power, let's say this is the power you normally receive. Then you have some kind of shadow fading effect, right? You have some shadow fading, and you want this to be, now this, note that I have not written a bar here. I have not written the average here. I'm just trying to understand the concept. So if there is some power at which I'm receiving the signal, and I'll bring in the averaging part later, and there is some additional fading for outage. What I need is this fading, right? Let's say this fading is subtracting, like some subtracting fading terms there. So this is all in dB scale, right? I'm doing all this calculation in dB. So if there is some fading which is taking away some dB power, I don't want it to fall below my Pmin. I don't. So I so if this receive power minus fading, so this is like this is effective receive power. If due to fading this effective receive power falls below receiver sensitivity, this will lead to outage, right? This is how outage can be defined. That if so, what I want to find, if I have to compute probability of outage, so it has to be probability is equal to prob uh, probability of equal to probability of f being greater than PRD minus Pmin, right? So this is the probability of outage, right? Now, probability of outage is probability of f being greater than PRD minus Pmin. Now we know that the fading, this in decimal scale, this is log normal shadowing with mean zero and with mean zero and standard deviation sigma. And this we can approximate it as the average received power at the cell edge. So this is nothing but the Q function of, so this is both in dB scale. So here when I write it, this was in linear scale. So if I write it in dB scale, then this is same as the quantity beta, right? So this is probability of f greater than beta. So this I'm just denoting here. This is in dB scale. So in dB scale, this is nothing but this is PR10 in dB minus this just subtraction in dB scale. So here this I just need f to be greater than beta, but then so this is in dB scale. So this is essentially 10 log 10 of PR bar D in linear scale minus 10 log 10 Pmin in linear scale. So if I have to write this in linear scale, and so this is probability f greater than beta. And so here if I, instead of dB, if I put these in linear scale, if I put the powers in linear scale, so then I get f greater than beta, which is the fading margin that I've calculated above. And this is, since f is normal, is a log normal shadowing of mean zero and sigma. So this is nothing but so probability. So what is the probability that f greater than x? So this is the Q function of small x by sigma, right? F greater than beta is nothing but Q function of beta by sigma. So I can just substitute Q function of beta, which is 0.212 divided by sigma. Sigma is denoted as 2 dB. So 2 dB is 10 to the power 0.2. So this will be my answer. Whatever is the value, that will be my answer. So I hope this makes sense. Let's see what the answer is and if it is something that can be calculated. Q function you typically cannot calculate, so you have to use calculators, online calculators. Okay. And somebody tell me the answer. I am getting it to be this weather. 0.44. 449 or 0.45 or 45% outage probability. So pretty high number. Okay. So I hope you understood the concept that so for fading for outage, we need fading to be such that it brings down the receive power to below the receiver sensitivity level. So this is really the definition of fading. From here we can solve the problem. So if we take f to the other side, then we have f is greater than the receive power minus the receiver sensitivity. And this margin in dB scale, we can calculate. This margin in dB scale, we can calculate based on given values. And like here it's given that the cell edge is 1.05 times the receiver sensitivity. And so we can calculate and then we can just plug in the values. So then you have f greater, you need the probability of f is greater than beta, which is q of beta over sigma. Which is the second important formula that you will need to solve this kind of a problem. And then you can solve it. So there were some questions based on this concept. Okay. So
Sir, will you please show the upper part?
1 second.
Starting part of the problem. Yes, sir. Just a minute, sir. I'm just noting it.
I will share the notes, so you don't really have to note it.
So today only will you share it?
Yes, I'll share it today.
Okay. On our assignment page only, no?
Yeah, I share it in a drive link, and I think the drive link is shared with you. So
YouTube link you will share.
yeah, YouTube link also I'll share today, and like this drive link also. And drive link is already shared with you, I think. So it is the same drive link. I keep on updating whenever I take a session.
Where it is shared, sir? Drive link. Will you show it, please?
It should have been shared by NPTEL team. I don't know. It's there on my own drive. So I can share the drive link in chat, but I believe it is already shared with the students. Because we have been asked to use the same link, so we are using it. So I'm sharing it in chat, but I believe it has already been shared with the NPTEL students. The same way you are getting information about this. I'm not sure how it is happening at their end. We are doing what we can. We have been asked to create a drive link and upload and provide them the drive link, and so that we have done. And YouTube links also we are sharing. So every week we upload YouTube links. So now I'm not sure what's going on in there. I can. I Anyway, I'm sharing the YouTube playlist link here as well, but it should have been shared by entity itself. This is the whole playlist where I'll keep uploading videos. So this week's recording will also be uploaded. So you are sure I did. You're not needed to take notes. Yes, we will make it all available. And some questions are very textbook style, but let me try and cover one type of problem. Uh, so let's say you have something like this. Let's do a little different kind of problem now. You have a mirror, let's say, right? And then you have a transmitter and a receiver. And the transmitter is moving towards the receiver at a speed of v meter per second. Right? At a speed of v meter per second, and this distance is d, let's say. This distance is r0, let's say. The distance between tx and rx is r0, and the tx is moving towards rx at a speed of v meter per second. Right? So your question is, okay, let me just, instead of the transmitter, let's say the, doesn't matter, let's say the transmitter is v meter per second. So you're asked to write equation of received signal. Received signal. So this is the snapshot at time t equal to 0, let's say. And you're asked to write equation of received signal at time t, some general t. How do you do it? How do you do it? So equation of, let's say, E field, the electric field of the received signal. So if we are specific about the electric field. So for this kind of question, we typically assume some kind of, so if you remember electric field, the unit of electric field is volts per meter. So it is inversely proportional to the distance. And let us assume for this kind of problem, typically you will assume some constant potential velocity v equal to alpha, let's say, right? So you have to find the received signal. So your received signal, E received, will be equal to E transmitted plus E transmitted plus E reflected. So you have two components. One signal is coming directly from transmitter to receiver. Another signal will go from the transmitter, hit the mirror, reflect back, and then reach the receiver, right? And then we kind of receive the receiver. So you have two components here. right? Or let me call it E instead of transmitted, right? Both are transmitted. So this is E direct. So one is from the direct path and another is from the reflected path. Just to give an intuition on how reflection works. So, okay. So here, the distance between let us first write down E direct, right? E direct as a function of t. So all of these are functions of t. This two plus E reflected as a function of t. All of these are functions of t. So the E direct is nothing but this constant alpha divided by the distance traveled at time t. So that the distance traveled by the direct wave at time t. So the direct wave travels a time distance of, it will be r0 minus v times t, right? Because at t time, this will have come vt distance closer. So you will have r0 minus vt distance left for the direct wave. So that is the distance it is left to travel, right? And for the phase part, it will have cos of 2 pi. So we are talking about real part of signal here, fc 1 minus we are trying to compute the phase shift, right? Your phase shift is this quantity, right? So how is phase shift into the picture? Let us multiply FC first, right? So firstly, you are having your direction of transmission of electromagnetic radiation is in this direction, right? From Tx to Rx. And the movement is also in the same direction. So that means you will get a kind of a negative Doppler shift. So like your Doppler shift value will be V by C times T, which is V by C times T cos 0, because it's in the same direction. If it were in opposite direction, then it would be minus V by Ct. So this is one Doppler shift that is happening. So this is one source of shifting, and another source of shifting is the phase shift due to the distance traveled, right? So at this, so when the transmitter is already here at time t, having traveled distance vt, the receiver is receiving this radiated source, which has traveled a length r naught, right? So this is like fc minus fd, which is this thing, v by c times fc actually, and then you have, so your phase will be then 2 pi fc minus fd of t. So this is one source of phase shift. And then you have another source of phase decrement, which is 2 pi times r naught by lambda. And lambda is c by carrier frequency, right? Because c equal to f lambda. If you substitute, you will get, if you substitute and I keep fc, if I take fc common, then I will get something like 2 pi fc 1 minus f d by fc, so which is v by c times the time minus then I'm again taking 2 pi fc common, so it's r naught divided by lambda times fc, which is c. So you can try and do this derivation, but this is the direct wave. And then the reflected wave, at time t is equal to alpha again. Let us try to see the time traveled, the distance traveled at time t by the wave already. So that distance traveled is, if you see this diagram, this will be r naught plus d plus d. So r naught plus 2d, right? And then a minus vt because it has already traveled vt distance. So 2d plus r naught minus vt times cosine 2 pi fc, and then there'll be a minus because the reflected wave is actually coming in the opposite direction. The reflected wave here is coming in. So if the transmitted wave goes here, the reflected wave is coming in this direction. And that is opposite to the direction of motion. So in this case, the Doppler shift will be minus v by c fc, because the motion of the wave is the motion of the source and the motion of the wave are the opposite. So I'll have something like cos 2 pi fc 1 plus v by c t, and then the rest will be the same, minus total distance traveled, so r naught plus 2d. The rest will be exactly the same, 2d plus r naught by c. So here in the phase part, we are taking the distance traveled at that particular snapshot. It is r naught plus 2d. So then, and the minus sign here, is because of this is reflection happens at the reflecting surface of glass. So this is reflection, which implies phase shift by 180 degrees. So hence you have a minus term coming in. And if you add both of these parts up, if you add the direct part and the reflected part, you get your answer. And then using this, you can kind of answer any question. I hope this is clear. The rest of the questions are pretty much theoretical or similar to this, or same in concept to this. So if you have any specific doubts, I'll answer. 1 second. R0 plus Vt or R0 minus Vt? That was the question by somebody, Beliga. I believe in this question, it should be R0 minus Vt, because the distance that you're traveling with the wave, that is decreasing. And so you can see that transmitter is moving towards the receiver, so the distance traveled is Vt by the transmitter itself, and so what you have left is R0 minus Vt. Okay. And the third question is, sorry, fourth one. Okay, so the other is a more straightforward, like not straightforward actually, it's more like derivation. Like. So, in case anybody has any questions, I would like to take them now. I think I'm almost done. Let me just do one Doppler effect question, which is one second. Let's say you are putting like some kind of like you have a simple pendulum setup, simple pendulum, right? And you have some kind of device here, some kind of, let's say, mobile phone, some antenna here, right at the base of the simple pendulum. And you are rotating the pendulum, right? Okay. So,
Sir, excuse
yeah,
me, sir.
yeah,
Sir, regarding this earlier problem, third
yeah,
one,
yeah,
sir, these are the equations which are the standard equation, no? E direct and E reflected, which we are getting, which we are writing here.
yeah,
So these are the standard equations for electric field in free space.
yes, yes,
Okay. So we will, if any time means any condition is given, then we have to formulate, we have to bring change as per the conditions in this equation,
yeah,
and we have to show it. What is the final,
yeah,
what will be the final expression?
exactly. So you can have, let's say, instead of transmitter moving in this direction, in minus in yeah, in this direction. So I think somebody pointed out it depends on convention that R naught plus VT or R naught minus VT. So actually, yeah, like if you were right, actually, I think that if this direction is taken to be zero, if this direction is taken to be positive, then I think by convention, then this will become a wave in the minus V direction. So that way, this, but then R naught is also in the opposite direction. Yeah, essentially, you are right. This is in standard electric field, and according to the condition, uh, you have to change. That is true.
Huh, huh, huh. Okay, so
According
sir,
to the condition. Yeah,
then in this means E direct, in case of E direct, it will remain a standard one only, no?
Yeah, it should remain the standard one. Yes.
Hello?
Yeah, it should remain the standard one. Actually, you are right that uh, the it depends on convention. Actually, the direct wave is reaching the receiver from
Huh.
right to left. That is in the minus in the
Negative direction.
negative x direction. While
Negative X.
while the reflected wave is coming in the positive x direction, so
Huh,
the
huh, huh,
direction of waves should actually change. So
huh,
then this
huh.
should be, I think, if this is in the positive x direction, then this should be plus Vt and this should be minus Vt. So that change has to show in the wave direction itself. I think that way
Yes.
you are right.
Huh, huh, huh. Okay. Okay.
But
So, that direction, how it is getting reflected in this equation, sir, in case of E direct
or,
equation?
or probably this is correct because the denominator part is just like uh, like you have to subtract the distance. Direction part is predominantly being reflected in uh, okay. I think 1 second. Here it is. Yeah, I think it is reflected somewhat here, right? See, here the Doppler shift is minus v, and here the Doppler shift is in opposite direction, which is plus v. And that is because the direction of transmission and reflection are in. So here the Doppler shift is like the Doppler shift for this wave because of movement of source will be source velocity is in minus x direction and the wave velocity is in the plus x direction. So Doppler shift will be v by c fc cos of 180 degree, which is minus 1. So then this is how it gets reflected. So then that will show here that we have a negative, like there is a plus v turn here, right? That is so.
Okay. Okay. So FD will be minus V by C into FC.
Yeah.
Okay. And so that is coming in this part, means in
Phase part.
original equation of E direct, it is cos of
Yeah.
2 pi FC into in bracket 1 minus this 1 minus V by C.
Yeah. Because for the direct signal, if you see the direct wave that is coming from Tx to Rx, that is also in negative direction. And the
Yeah.
transmitter is also moving in the same direction. So your frequency is getting like reduced. So the Doppler shift is appropriately. So here the Doppler shift is plus V by C. Here the Doppler shift is plus V by C. So that is showing here.
Okay.
So that is
That
that is
that
where the
is
difference is
in case
coming.
of reflect. It is plus V by C in case of direct wave. But then direct.
Yeah,
Okay. But then why it is? It should be minus in case of
reflected.
a direct wave. It should be minus in case of direct only, na? No, no.
Huh?
Okay. Okay. So
One second.
it is moving towards receiver. So
Yeah,
Doppler shift should be 1 minus V by C, and it
yeah,
will be
yeah,
negative in case of reflected wave. So it is
yeah,
getting 1 plus V by C.
yeah. Because see, reflected wave here in the way I have drawn the diagram. See, the transmitted wave is hitting this mirror, and then it is taking a turn and going in the other direction. So
Yeah.
the reflected wave is coming somewhat in this direction.
Yes, yes.
While the transmitted velocity is towards the mirror. So then that's why there is a like this change. It will become minus -1.
Okay.
So,
Okay. And sir, what about this 2D plus R0 by C?
so this here is like
So D plus D. 2D.
2D plus R0 by C. So this is because of this phase shift because of distance, right? If an electromagnetic wave travels a certain distance, in general, if an electromagnetic wave travels a certain distance, then there is a phase shift of 2 pi d by lambda, right? Like this is the phase shift that happens. So, and now lambda is nothing but lambda is C by Fc, carrier frequency. So if you substitute that, then this will become 2 pi Fc. If you take common, you will have something like d by C. So this term you will get. Now this distance traveled in case of the direct wave is so like at the so here when you take the distance, the Doppler shift effect has already been taken into account. So now if you just don't take into account the velocity, the distance between source and destination is r naught, right? Here for the direct wave, and for the reflected wave, the distance will be r naught plus d plus d. So the wave travels r naught distance, then d distance, and then d distance back. So this distance becomes 2d plus r naught. So that is why you have r naught by c here, and then you will have 2d plus r naught by c here.
Okay, okay.
Then there is an additional phase shift of 180 degrees, because of which there is a minus sign. Because what we have here is a reflecting surface, mirror. So mirror produces, if you remember, mirror produces, like in the reflection theory, mirror produces a phase shift of 180 degrees, because it's solved by using those boundary conditions and all, and you can prove it. That mirror produces phase shift of 180 degrees. So then, so all of these things contribute. So then you have the directive and the positive.
Okay, okay. Okay, sir. Thank you.
So this kind of problems you can do, and continuing with this itself. The reflection causes phase shift by 180 degrees. So these are the. Now let's say you are asked for this wave, what is the Doppler spread? So you have a multi-part scenario here, two multi-parts. Okay. So Doppler spread is your. So this is defined as difference between max and min Doppler shift. Doppler shifts. So this is the definition. So you have two parts. So again, if I draw the diagram here, so if you have a Tx here, you had the Rx here, and you had this vehicle Tx moving at a velocity v, and this distance was d, this distance was r, right? So you have to find the difference between the maximum and minimum Doppler shift. So there were two waves. One was the direct wave, and the other wave was the reflected wave that was hitting this mirror and coming back. And so the Doppler shift in the first case was plus v by c f0. So let us write that down, v by c times fc. And let's take a so we just have two waves here. So let's take a difference between them. For the second wave, it was minus v by c fc, because there was a change in direction. And so if you take a difference, it will actually add in magnitude. And so you will have 2 times v by c fc. So as you can see, this is very much dependent on your diagram. So if you just change one thing, like if you make this transmitter move in the opposite direction, then everything will change. If you interchange position of Px and Rx, everything will change. I'm just trying to show the method that you will use, because in exam you can get any kind of diagram. So once you get this equation right, the direct and the reflected wave equation right, then everything is followed. So again, the Doppler spread here is, you will have two waves. You will have direct wave, you will have reflected wave. And so you just have to take the difference of the Doppler shift. So this is, let's say, FD direct, and this is FD reflected, right? So you just have to take the difference in the Doppler shift. So here in this case, it will be, actually difference will be addition magnitude. And so you will have 2 times V by C, right? And then let's say you are asked, when there will be, so you are asked a condition for constructive interference, something like this, right? So you have two waves, one direct wave and a reflected wave, and this is reflected. So when will they constructively interfere, right? For constructive interference, you need that the phase difference should be any answers? The phase difference of the two waves should be this 2n pi, right? Phase difference of direct and reflected wave should be equal to 2n pi. So that is constructive interference. So what is the phase difference? Let us compute that. So phase of the first wave here is this one, 2 pi fc 1 minus v by c ft minus r naught by c, right? So let us write that down. This is just algebra at this point, but so this thing. And then the second wave is the second wave phase is phase again, not the magnitude. It is 2 pi fc 1 plus v by c t minus 2d plus r naught by. 1 plus v by c times t minus 2d plus r naught by c. Okay. And then let us add a phase shift of one second. Let us see how to do this. Okay, so and also remember that there was an additional phase shift of pi here because of reflection, right? So this minus term in magnitude is actually a phase shift of pi. So this is also there. In the reflection, this is also there. So then this has to be equal to 2n pi, right? So then if you solve this, 2 pi fct will get cancelled, and what you will be left with here is this 2 pi fc times 2 minus 2 v by c t, I believe, plus 2 pi fc 2d by c, right? Because r naught by c will get cancelled. This is 1 by C and 1 by C will get cancelled. So we'll have something like this. And uh, this will be equal to 2n plus 1 pi, where n is belonging to whole numbers, right? And 2n plus 1 pi, so this is like, if you cancel out pi everywhere, then you will have what will be the final? You will have something like, to cancel out pi everywhere, then minus 2 4 d fc by c, or like, okay, it's 4 fc by c d minus vt has to belong to 2n plus 1, which is essentially set of this is essentially like, if you put various values of n, this will be minus 3, minus 1, 1, 3. So this will be set of odd integers. Odd integers. 4fc by c d minus v. So this is for this. So this is your final condition, that 4fc by c d minus vt must belong to the set of odd integers. In that case, we will get like perfect constructive interference. Something like that. Okay. So Raishan feeling, Naparami feeling, I will come to this. Let me just finish one more small nugget of this. That
Excuse me, sir.
then, yeah.
Sir, how these integers have come? Minus 3, minus 1, 1, 3.
Simple. 1 second. So these integers. So you got this condition, right? That phase difference has to be equal to 2n pi, or so this is the condition for constructive interference between two waves. If you have two electromagnetic waves, their phase difference has to be like psi1 minus psi2
pi.
has to be, yeah, 2n pi, where n is essentially, n belongs to I, right? So n belongs to I, where n can be any integer. So you just need it to be an even multiple of 2 pi, right? Now, from that, solving this, we get this final condition, right? For so 4fc by c d minus bt equal to 2n plus 1. And now if you put n belongs to integer over here, so then what are the values you can get? If you put n equal to 0, you will get 1. N equal to minus 1, you will get minus 1. N equal to minus 2, you will get minus 2. So if you put integers like that, then this is nothing but the set of odd integers, right?
Okay,
This
okay,
is
sir.
a set of odd numbers. So that is all. So your condition is that this term 4fc by c d minus dt has to be an odd number. And if this is an odd number, then your interference will be like purely constructive. Right?
Sir, why it has come 2n plus 1, sir? 2n plus
2n
1
plus
into
1,
5?
because here there was when you are computing phase difference, there was an additional term plus pi, because in the reflected wave there is a phase shift by 180 degree, or pi.
Okay,
Phase shift
okay.
by pi, right? So that is shown by the minus term here, but if you bring it to the phase, term, then it will be cos of 2 pi plus 2 pi fc, right? That is cos of pi plus theta is cos of minus of theta. So,
Cos of
so
2
then
pi
that is,
fc. Cos
so
of
minus, yeah. So if you want to remove the minus, then you will have to add it over here, right? You have to add a plus pi over here, right? Or 1 second, minus. So if you want to, like, so this minus term is because of phase shift of 180 degree or phase shift of pi, right? Right. That,
Yes, sir, that is okay. So due
yeah.
to that, it has become 2n plus 1.
Yeah, because when I'm computing, so I'm taking phase difference between direct wave and reflected wave. So here in reflected wave, I'm
Uh,
writing whatever is here in this term, but then I'm also adding pi to it because of this minus. So here I've written an extra pi, and then if you break the minus, then you will have minus pi, and you put the minus pi to the other side, you will get 2n pi plus pi, or 2n plus 1 pi, right? And then you cancel pi from everywhere, and then you will get 2n plus.
okay, okay, okay. So after calculation, it is coming out to be 2n plus 1 pi.
Yeah, simple, right? Like here in reflected wave, a plus pi is there. And if I break this and if I take this pi to the other side, then I get 2n plus 1 pi.
Ha, ha, ha.
Minus was there.
Okay, okay.
And pi cancel, then it's okay. So then the last thing that typically you can calculate is delay spread. So delay spread is difference between path delays, uh, time delays. So you have multi-path system again, one direct and one reflected, and you want to find out the difference in the time delay, right? So here the time delay is typically uh, is this term, that is like this. This is the time delay, right? The time taken for the wave to finally reach the transmitter. From transmitter to receiver, how much time does it take for the wave to reach? So the time delay in first direct wave is R naught by C, and in the second wave is it is 2D plus R naught by C, right? So then the difference between the time delays is 2D plus R naught by C minus R naught by C. So this will be 2D by C. So this is what we call as delay spread. So the direct wave takes R naught by C times to reach, and then the reflected wave takes 2D plus R naught. So that added distance 2D shows up in the delay spread. So this is like the difference between the delays. So that is all. Okay, there was a question now. Raishan fading, Nakagami fading. Okay, Raishan fading is simple. Here, Raishan fading is essentially when we are viewing the channel as a line of sight channel plus a non-line of sight channel, right? So here, let's say the channel gain is something like beta, something like, let's say beta. So, and there is a Raishan K factor K. You are told that the K factor is K. So how will you write this? Let's say it's a simple single antenna channel. I'm not going into multi-antenna now. You'll be writing this as K by K plus 1 root over beta plus 1 by root over K plus 1 some H tilde, where H tilde is complex normal. So this will be your Raishan channel. How is this Raishan? So this part, if you just isolate this part, so this is Rayleigh distribution, right? And we all know Rayleigh by now. So this is Rayleigh distribution. A question on Rayleigh distribution is there in the previous week's assignment, and important. So this is the Rayleigh distribution where we are representing channel as a fading channel. So the mean is 0, and there is a standard deviation beta. So, now, if it's not a purely fading channel, right?
Sir,
then
why it
we
is
can
Rayleigh
use
fading? Sir, why it is Rayleigh fading?
Rayleigh fading is a model that is used. So it has been found to fit actual channels quite well. So that is why Rayleigh fading model is used. These are all models, right? Like if you want actual channel measurements, the only way you can do it is to actually go and measure. But people have done the measurements, and widely in literature, Rayleigh fading model is being used, especially for low frequency channels. Rayleigh fading model works quite well. But if you move on and on to higher frequency channels, especially millimeter wave infrared, Raishan fading and Nakagami fading are more accurate. So what Raishan fading tells you is if you define a certain K factor is nothing but power of the line of sight component divided by power of the non-line of sight component. So you are assuming that the channel has some line of sight component, some non-line of sight component, and their powers are in the ratio K. So if you can see that the line of sight component power here, PLOS here in the model that I've written, it is K by K plus 1 times beta. You just square this part, right? So this part is constant, it is deterministic. That is, line of sight part is always constant. Deterministic, it's not a random quantity. And then you have the random quantity, which is a non-line of sight part, but the power for that is also known. You just need to take a norm square of this term and expectation over that. So that will be 1 by K plus 1 times beta, because expectation of norm h square, mod h square, it is complex normal 0 comma beta, so it will be beta. So if you take the ratio of PLOS upon PNLOS, you will come with, so you will get Raishan K. And now depending on K, you can choose your model. So if you take K equal to 0, then what you will have is this line of sight part is 0. And so you will have pure non-line of sight. So this is actually Rayleigh. So pure non-line of sight where your channel is completely like a zero mean Gaussian channel with a certain variance, that is Rayleigh fading, pure Rayleigh fading. Then if you go the other extreme, if you take K infinity, right? If you take K infinity, K approaching infinity, then the non-line of sight part goes to 0. And so what you have is a almost pure line of sight channel, pure line of sight channel. So then this is pure, line of sight. So pure line of sight channel is also used in many situations, especially for high frequency, like millimeter wave terahertz frequency channel. And so the Raishan fading model allows you to choose, choose something that is intermediate between the two extreme assumptions, which is non-line of sight and line of sight, by varying this value K. So if you put K as some intermediate value, then like let's say K equal to 1 if you put, then you will actually have like perfect balance PLOS equal to PNLOS, right? And so you can see that this will become 1 by root 2, this will also become 1 by root 2. It will be like half division. So this K value is actually defined in like 3GPP. You might have heard of it, 3GPP standards. So depending on your situation, whether you are simulating a rural environment or an urban environment or indoor or outdoor or whatever, according to that, you need to appropriately pick the right value of K as defined in the 3GPP standard. So that is, Raishan fading, right? And, uh, Nakagami fading is different. So in Nakagami fading, you model H as a what they call as this. So where so this is known as a normalized gamma. Normalized gamma random variable, right? So gamma random variable is actually like this. I can pull it up 1 second. So
Sir, is this PLOS equals to PNLOS is Raytheon fading example case?
yeah, this is Raishyan fading example that if you take k equal to 1, then so that is one case of Raishyan fading, right? You can take k equal to 1.
Okay.
So then you like then you get one situation where line of sight and non-line of sight parts are like equally strong.
Uh-huh.
Okay. So I can yeah, so then that is uh, so then this is actually like so there is for gamma variable 1 second. Uh, you can check size lectures for like a more accurate definition that is used in the class. But typically, like this is written like this Nakagami M, where this M parameter is the really important part. So the PDF of this distribution is something like um, M, and this this is given something like 2m to the power n by gamma n. Something like this. But essentially, the key concept here is that this is also somewhat trying to, like, similar to Raishian. Like, Raishian uses this K factor to tune between, like, tune between your this thing, um, tune between LOS and NLOS, right? So it depends on your K factor whether you will have LOS or NLOS. Now here it is tuning of M factor that determines whether you have LOS or NLOS, right? So tuning of M factor here. So typically there is a relation between your uh, right, uh, 1 second. So then this so there is a relation between the M and the K factor I'm forgetting it at the moment, but it is there in such lectures. And so that relation you can use. So I believe there in such lectures. But anyway, so m equal to 1, remember m equal to 1 is essentially your essentially this is equivalent to k equal to 0, which is pure Taylor. So the basic idea is the same. It's just that in some cases, uh, the Nakagami M distribution is like the Nakagami M distribution is a better model to choose in certain settings where like where Rician is not sufficient, and in some cases Nakagami M is more analytically tractable. So you can use the Nakagami M model to obtain nice expressions in closed form, which you cannot obtain with Rician filling. And in some ways, you can establish an equivalence between Nakagami and Rician. That if you have, so there is a relation between the Nakagami K factor, with Nakagami M factor and the Rician K factor, and so you can use that relation to generate equivalent your distribution. We got that relation just now. So that relation is somewhat like k plus 1 by 2k plus 1, k plus 1 whole square by 2k plus 1. So it is somewhat like this. So if you put, let's say, as you can see, if you put k equal to 0, you will get m equal to 1. And so depending on that, so you can also have any random k. So k equal to, let's say, 10 dB, which is equal to 10. So then your m will be equal to 11 squared by 21, and you have to take the closest integer to it. So m is actually a factor that has to be integer. That is something that makes me determine. Actually, not integer, has to be natural number. So otherwise, this gamma is like tricky to define, gamma distribution. So you'll typically take the nearest natural number. So that is there.
Sir, I have a question. In these different models of distribution, what we
Okay,
are
so one question was there, like Raishan and Nakagami M are similar. Yes, they are similar. They use the same idea, but they are not exactly the same. Also, it's just they're mathematically they are different probability distributions. They have like if you plot PDF, they might look similar, but sometimes in calculations, Nakagami M is a better alternative to use, especially in like academic papers and calculations. But in 3GPP in standards and actual implementation, Rician is mostly preferred because it is more intuitive to understand also. Like you have a clear line of sight and non-line of sight part, and so it's like very, very easy to understand. Nakagami M is a little complicated and it's not that easy to understand. Yeah. Sorry, continue.
Yeah, sir, in these different models of distribution, we are
Yeah.
analyzing how the power is distributed in that overall area.
So you are analyzing how the channel behaves in some sense, like how your signal will fade from transmitter to receiver. That is what you are trying to analyze. So one part of that fading is your large scale fading, or your, like, firstly your path loss will be there. If I go back to the very first model,
Yeah.
so firstly your path loss will be there, which is the straight line. Then path loss plus shadowing also you will take into account, which is this more stable curvy line. And then the very unstable line is when you also bring in small scale environmental fading coefficients. And now that is why now to model this behavior of the channel, because not every time when you are doing simulations, you cannot always take channel measurements and then build your model. So you kind of assume some kind of mathematical behavior, right? And so these assumptions have been made in literature. So starting with first crude assumption is your AWGN channel, where you are just adding some noise, and then you have this fading effects that were considered. So then you have relay fading, that's what you study first. And then you have these more sophisticated fading models, that is Raytian, which is, you are considering that the channel has this static, constant, non-random or deterministic part, which is your line of sight part. And then you have a random part, which is non-line of sight. So that is
Non-line of sight path.
yeah, so that is your
Yeah. So,
Raytian channel. And Nakagami M is another variation of the same idea. It's a little less intuitive, but it also roughly does the same thing. So depending on value of M, your M equal to 1 is the lowest value that you can have. So that gives you pure relay channel or non-line of sight channel. And if you take M higher and higher, you will approach like line of sight channel. So
M is
that is
less
how this
means it is non-line of sight.
yeah.
Okay, and M is more means it is line of sight. But
Yeah.
means, sir, we
So if
are
you just try putting, let's say as an exercise, you put M equal to 1 in this PDF, what are you getting? Gamma of 1 is 1, I think, right? So you will get something like 2x e to the power minus x square. And this is Rayleigh fading, right? This is
okay.
the Rayleigh distribution. So
Uh-huh.
so then higher the value of M, you can show that this will become more of like pure line of sight. It will actually approach a constant value or something like that, some kind of delta function or something. So
So what does M indicate, sir?
M is just a parameter, like your K. So these are things that you can vary depending on your condition, channel condition. You can vary them, M and K.
Yeah. So what we are thinking about is how the power is distributed in that overall area. What I asked earlier.
So how, yeah, somewhat that you are trying to figure out how, like, so in any signal that is
Fading will
traveling,
occur means strength of the signal will become less.
yeah,
So
yeah.
how the
So
strength decreases? Is that analysis means this Russian model and Rayleigh
yeah,
model?
so you are trying to see how this channel is behaving, right? So if
Yeah.
you're like you are trying to see how much of the received signal will be from the line of sight component and how much of it will be due to scattering in the environment or the
Ha.
non-line of sight component. So that is what you are trying to see. So if you have a rich scattering environment, if you're using low frequency signals and it is being scattered in all directions because of environment and all that. So you have a lot of multipath, then you will have more of non-line of sight path. But if you are
Ha.
using high frequency signals with pencil beams, like directed beams, then you will have a predominantly line of sight channel. Like non-line of sight part will be negligible because in the environment, whatever goes out actually it deteriorates signal quality. Like the non-line of sight parts essentially dissipate their whole energy because as we go higher in frequency, the as we go higher in frequency, it is more difficult for signals to travel far. So only the line of sight component, which is very well beamformed and very well directed, only that part has strong enough signal to actually reach the receiver. So you have a pure line of sight signal. So
And
that
non-line of sight path will face more and more fading due to different reflections
yeah,
and scattering.
yeah.
Okay.
So
Okay, so we
that
are
is
discussing that only mathematically, how they are
yeah,
getting faded
yeah. So
through this.
in a Raysian channel, basically you will have one part that is constant that won't be subject to fading that much.
Okay,
And then
so
you
that
will
is
have
line of
another
sight.
part
That is line of sight. That is line of sight, sir.
that is the line of sight.
Which will not change, which will not face fading.
Yeah,
Okay. And second part is it will face fading.
yeah. With this way.
Okay. Okay, sir.
So,
Thank you.
any more questions? Thank you. Then I'll end the session. You will have notes and everything.